everybody. Thank you for coming to this presentation, everybody that's joining us both remotely and here in Boulder, Colorado. If anybody has questions and they're shouting them at their screen remotely, I cannot hear you. So please type them into the chat and I will get to those questions maybe throughout the talk, but probably mostly at the end of the presentation. So today I will be going over hyperspectral imaging. So I'm going to give a brief introduction to hyperspectral imaging. I like to call it Hyperspec 101. And then I'm going to give a live demonstration of Headwall's lab scanning kit. And during the live demonstration, I will turn on a webcam so people joining us remotely can also see what I'm doing. And then I'm going to talk about some recent results that we have gotten in mining partnerships. So scans that were taken over basically places with interesting mineralogy. And finally, I'm going to talk a little bit about Headwall's integration of hyperspectral imaging and LiDAR, and some of what we're doing with the fusion of data between hyperspectral data and LiDAR data. So again, thank you everybody for coming, and off we go. This is the outline of the talk that I just sort of went over, so I'm not going to spend much time on this, but I will also say at the end of this presentation, anybody that has taken the time to come here, I'll be happy to give you an opportunity to get your hands on our starter kit. If you have any samples you'd like to put under there, go ahead and put them under, we'll scan it, and if you have a flash drive, I'll even send you home with the data. And also any other questions that you might have on other areas of hyperspectral imaging applications or LiDAR data collection, I'll be happy to answer those too. So starting off, as you can see from this picture here, the electromagnetic spectrum covers a wide range of things, all the way from gamma rays, X-rays, out to radio waves. So most of Headwall's products concentrates on the part of the electromagnetic spectrum that's illuminated by the sun. So there are a couple of reasons for that. First, of course, detector technology has developed a lot more around the area where we can see. And also, we deal with a lot of remote sensing products. And for remote sensing, the sun is a very convenient source of illumination. The price is right, it's pretty darn bright, and it turns on almost every day. So as you can see here, these black lines mark the area of the electromagnetic spectrum that is covered by Headwall's imaging spectrometers from the UV range all the way out to the shortwave infrared. And just for your reference, I've also shown between this purple line and this red line, the area of the electromagnetic spectrum that we can see with our eyes. And this green line here shows the solar spectrum. And these little dips in there are atmospheric absorptions. So this is the actual light that's hitting the ground with some little bits taken out of it because we have gases in the air that absorb a lot of that light. So here's just a brief introduction to the different sensors that Headwall provides and the spectral ranges that they cover, from the UV to the visible near infrared. Our most popular sensors are probably our V-near sensors that cover the spectral range from 400 to 1,000 nanometers using silicon detectors. We also have a couple of in-gas systems that cover what we call the near infrared range and the extended V-near range. And then we also use MCT detectors to cover the shortwave infrared all the way from 900 nanometers to 2,500 nanometers. So what is spectral imaging? How is it useful? And basically, what are the basics? What are we looking for and why is it important? So pretty much all objects will have a unique chemical fingerprint. So basically, it's how that object will absorb and reflect light will depend on the chemical structure of that object. So your table, your chair, the wall, it will all absorb and reflect light differently. And if we collect basically continuous spectrum, if there are unique spectral features in the spectral range that you're looking at, you can use those spectral features to identify different objects. So one example that we like to show a lot when we're showing off our SWIR systems is if I put a bunch of white powders under the SWIR system, by your eyes, they all look white, like baking soda, salt, sodium bicarbonate is baking soda, some white clay, but they will have different spectral features in the shortwave infrared, so they can be easily distinguished if you use a SWIR sensor. Just like there are many objects that might all appear green, like a leaf or grass or something like that, but they will have slightly different spectral shapes in the V-near range. And for this kind of simple example, I've shown 4 different things that all have very different, of course, spectral features. And you can tell by looking at these spectra that if you have these spectral shapes, it will be very easy for you to tell the difference between pine woods, grasslands, red sand pit, and silty water. So how exactly do our imaging spectrometers work? What's inside the box? What's under the hood? So here, I've kind of shown a little cutout of our imaging spectrometers, and they're all what we call Pushbroom or line scanning devices. So light will come in through this 4-optic lens. We will basically gather the scene, and then that scene will be re-imaged onto this slit, but we will block out all of that scene except for one little slit of the scene, one sliver. And then that sliver of the scene will be re-imaged onto the focal plane array. So using what is called the Offner relay. And a normal Offner relay will just be a 1-to-1 imager. So it would take this slit, it would put it on this focal plane, and you would just basically reproject this slit onto the focal plane, and you'd have one little line across the center showing that scene on the focal plane. However, we have slightly modified the standard Offner relay by making this second convex mirror a convex diffraction grating. And that diffraction grating will disperse the light in the other dimension and fill up your whole 2D focal plane array. So basically you have one dimension of spatial pixels and another dimension that we call our spectral dimension of spectral pixels. And I like to think of this as having something like 640 spectrometers inside one box. So each of these spatial pixels will get a complete spectrum, and we'll fill up pretty much the whole focal plane array. And for every snap of the camera, we will get a spatial line and a spectrum for each of the pixels in that spatial line. And I'm going to show a few other images to help explain that a little bit better. What I've shown here is a picture of what the scene might look like with everything blocked out except for one slit. So every time the camera takes a picture, we're just getting one sliver of the scene. And so this is what it would actually look like on that diffraction grating, or on the focal plane, if we did not have the diffraction grating in there. So if we were not dispersing the light, we would just put this one row of pixels back onto the focal plane. But we are dispersing the light, and so then each of these spatial pixels is dispersed spectrally from blue, green to red, and we will get a spectrum for each of these spatial pixels. And our standard spectrometers will have a lot of times 640 spatial pixels. So that's why I say it's like having 640 spectrometers in one box. So how do you collect a whole scene? How do you build up a data cube? When we are talking about hyperspectral data, it's often popular to talk about the so-called data cube. And so a hyperspectral system will collect 3-dimensional data. There will be 2 spatial dimensions and 1 spectral dimension. So I guess the easiest way for me to visualize that is any picture that you take is normally a 2-dimensional picture. You have an X dimension and a Y dimension. You have 2 spatial dimensions. And so you will get just a 2D image, and a hyperspectral image will have a whole spectrum at each of those spatial pixels. And so you can kind of think of that as being this 3rd dimension in your data cube. Well, of course, you only have a 2-dimensional focal plane, so you kind of have a problem. In order to collect 3-dimensional data, you need to scan something. And Headwall has chosen to scan the other spatial dimension. So every time we snap a picture, we get one spatial line and the spectra for each pixel on that spatial line. And then as we push broom across the scene, that's why I call it a Pushbroom sensor, every time the sensor moves one spatial pixel, we snap the camera again, we snap the camera again, we snap the camera again. And so eventually we push across the whole scene, and we gather a 2D image with spatial and spectral information at every pixel. And so again, every time the camera snapped, you'll get one of these pictures here. The direction of motion is this direction. And so of course, like I said, you need motion somehow. You either need to move the scene past the camera or the camera past the scene. For remote sensing cases, it's a lot easier to move the camera on, say, a drone than it is to move the Earth. So we decided to move the camera. But for, say, a lab system, it's actually easier to sweep the sample past the camera than it is to move the camera. So like you can see here, my camera is mounted in a stationary position, and I will move the sample across the camera. And again, every time the sample moves one spatial pixel, I will collect a new frame, collect a new frame, collect a new frame. And building up all of those frames, I will get my data cube. Another thing that I like to mention to everybody, and this is the case for any imaging system, any sort of remote sensing system, there will always be a trade-off between resolution and your field of view. So we have 640 spatial pixels, say in our standard camera. So you can divide your scene into 640 different little bins. If those bins are larger, you can cover a larger area. If those bins are smaller spatially, then you can get higher resolution. And so if you want to cover a lot of area, you will necessarily need to either sacrifice resolution or scan much longer. But if you want to have higher resolution, you'll have to sacrifice some of your swath width. And I like to show this little illustration here as kind of an example of one way that you can play with your flight altitude to tweak your spatial resolution. So these two different triangles that I have here represent two different lens focal lengths. So a shorter focal length lens will provide a wider field of view, will have a wider angular field of view, and a longer focal length lens will have a narrower field of view. And so what is called this angular field of view will remain static based on your lens choice. But if you change your altitude, you can change the amount of the scene that you're covering. So of course, at lower altitudes, you will cover a smaller bit of the scene at a higher resolution. And at higher altitudes, you will cover more of the scene, but at lower resolutions. So that's just one way that you can easily, using just a standard drone, you can choose to fly at, say, 20 meters or 120 meters to either get better resolution or to cover a larger swath. So now we're going to switch over to the live demo now. And I'm going to pull up my remote desktop connection. And so basically, I'm just remote desktop connecting into this computer that controls the camera and everything, and pulling up our data collection software. So right here, this is our standard data collection software. And the workflow is basically we just go through all these buttons. So start off with the live view. The live view on this part right here will actually show the whole focal plane array, so you can see every pixel in the focal plane. And if I show my crosshair right here, on the cutouts right here, I'm showing this spatial line and this spectral line. So the sensor that I have up here is our SWIR 384 shortwave infrared sensor. So it goes from 900 to 2500 nanometers. The light source I have here is a quartz tungsten halogen lamp. And so that's why you're seeing, of course, we don't have the same amount of light at every pixel across the whole spectrum because the quartz tungsten halogen lamp has its own spectral response. So you can see right here what the spectrum of my light source looks like on my sample. So I can pull up the motion tab, and this will allow me to move my stage back and forth as I'm setting up my sample scan. I also have a calibration tab here. So, and I'll talk about this a little bit more after this live demo, but the sensor will always just detect how much light is getting to the sensor. What we ultimately want, normally in the hyperspectral imaging world, is the reflectance data. The amount of light reflected divided by the amount of light that's actually hitting the sample. And so that will be the relative amount of light that's reflected from your sample, and that is where all of the chemical information is contained. And so that's really what we want to get to. But we're always just measuring how much light is actually getting to the detector, which, as you can see, depends on your light source. It depends on the optical characteristics of your system. It depends on a lot of things that aren't the sample. And all we care about is the sample. So the way, at least in a lab setting, that we calibrate that is right now I'm staring at a piece of Spectralon. And this piece of Spectralon has a very high reflectance across the whole spectral range. And I will gather what I call the white reference. And this white reference is going to be a hand-waving estimate of how much light is hitting the sample. So if I'm hitting a target that reflects almost all the light, I can fairly closely assume that that is how much light is hitting my sample. And now on this calibration screen here, this is a histogram of all of the pixels on my sensor. And this is a 16-bit sensor, which saturates at 65,536 counts. And so I can see that I don't have any pixels that are saturating. And so that gives me good confirmation that I've properly set my exposure. But I am filling up most of the well depth of my camera. So my light isn't way down here. And so now I'm just going to quickly click collect white reference. And this is going to gather the white reference. It's actually collecting 100 frames and averaging them together to give the white reference. And I also will collect the dark reference. The dark reference is just a way to get the sensor response when there's no light on the sensor. So of course that must also be taken into account because there will be some sensor response when no light is hitting it, and we just want to subtract that away. For the SWIR sensors, we do have an internal shutter. So if I just click collect dark reference, you'll hear a click. That shutter will close, and now I'm collecting my dark reference. And so if we didn't have that shutter, I would need to put the lens cap on. And if I put the lens cap on, you could see on my histogram that pretty much all of my pixels have very low counts. And so that's what I just gathered in my dark reference. Another window that we have here that is very handy, and I'm just gonna get rid of the live view, is this waterfall image. So remember again, we are a line scanner. So at any given moment in time, we're only seeing one sliver of the image. But to kind of get an idea of what our scan looks like, we show a waterfall display, which shows some history of the last things that were scanned. So if I put my hand under here, you can see my hand coming in and out, and now my hand is out, and now we're sitting on the white tile, so we're only seeing white. So if I move my sensor across my field of view, I will see the rocks on here, and it will build up on the waterfall display. So if I just go into my motion tab, and let's move 230 millimeters away. And so now if you can see the stage, it is moving. And as I move the rocks past the sensor, it's going to collect one line of the rock at a time. And in our waterfall display, we see some history there. So we're going to see what the sample looks like. And so this is just a nice way to make sure before you collect data that your sample looks like what you expect it to look like. One other thing that I forgot to mention that I did already take care of before everybody got in here is, again, remember, because we are a line scanner, we need to collect a new data queue or a new frame every time we move one spatial pixel. So basically, we need to match how fast we're going with how fast we're collecting data. In order to know how fast I want to move, I want to know how big one spatial pixel is. And one way that I can do that is we have built into our software, if you put a target with 1 centimeter space lines, it will calculate basically how large is one spatial pixel. And then using your frame rate, it will calculate how fast you need to go. So if I go to my capture tab, so this is where I set up the data collection. If I just hit this little calculate button, it will assume that it's looking at a target with 1 centimeter space lines like it is, as you can see on the waterfall display. And it will take my frame period in and then use that to calculate my speed. And of course, the speed didn't move because I already did this, but I guess I can demonstrate. So I'll change the speed to 5, which is not the correct speed. And then I'll hit the calculate button, and it will update the speed to the proper speed to get square pixels. So now, the other parts of setting up this capture tab, again, I kind of cheated and took care of already, but usually I would move from one end of the sample to the other end of the sample while looking at the waterfall display to see where does my sample start and where does my sample end. And that's how I would set the start position and the stop position. I guess, well, while looking at the live view and the Spectral on, I would usually adjust my exposure time in order to get the right level of exposure, so I'm not saturating anywhere, and so I'm getting a good amount of signal onto the sample. But again, I took care of all of that before everybody came in. But after the presentation, if anybody wants to do that themselves, by all means they can. We can set up new scans. Again, like I said, you can scan your own stuff. You can take home some data. But now, I'm just going to finish setting up this capture, and we'll call this Boulder, LDR, Boulder 1. So we call this prefix because every time you collect a data cube, that data cube will be timestamped. So if you forget to change the name, you'll just have a bunch of things that are the same name plus different timestamps. So you'll never overwrite data. But the prefix of this data cube will be Boulder 1, and then it will be underscore in our timestamp. So if I now just collect go, I'm going to collect the data cube, and we can again watch the waterfall display as the data is being collected. And personally, I think this is a pretty fast way to get a bunch of spectral information from a scene. That was a pretty quick bit of data collection, at least to me, compared to some of the labs that I've been in. So now I'm just going to move the stage back to the Spectralon, because I like to sit on the Spectralon because this light can get kind of hot, and I don't want to get my nice black little stage nice and hot. So now we've basically finished the data collection part. So we have a data cube and we want to analyze it. So I'm going to minimize our data collection part. Oh, and I guess I've already cheated and opened that up a bit. But now I'm going to open our analysis program. So our analysis program allows you to view the data cubes. And so I'm going to open up the data cube that we just got, so Boulder 1. And every time you collect data, it will save a folder that has what we call the raw data, which is just the raw camera counts. If you've collected it on a starter kit, it will also save a file that we call data, which has already had the white and dark reference applied. So this has already been calculated as reflectance. And it will also have the white and dark reference if you want to do that yourself using the raw data file later. But just for brevity's sake, I'm going to open up the data cube. Now it will allow you to select how many of the bands you want to load. Sometimes if you have a very, very large data cube, you might not want to load all of the bands at once. So you could just select RGB. Of course, RGB is kind of funny in the SWIR because we're not collecting any red, green, or blue light. We're only collecting light between 900 and 2500 nanometers. So we've sort of arbitrarily picked 3 bands to call red, green, and blue. But normally, I would just press select, and it will select all of them. And you can see here how much memory is required to open this and how much memory I have on my computer. So I'm not very far on this green bar, so I'm doing pretty well. And there are some other kind of built-in features of how you can manipulate the data cube. But for now, I'm just going to, oh, actually I did that. Yeah, on this one, I don't want to flip it. So there we go. Here is our data cube that we just picked. And we can either look at an RGB value or a grayscale value. And so the grayscale value is just going to be the intensity at any given spectral band. So all the way from 900 to 2500 nanometers, we can see the grayscale image of everything. Or the RGB, you can pretty much arbitrarily select any red, green, or blue pixel to project an RGB image. And so this is, again, just a quick way to visualize the data. But we have one other feature in the software that I'd like to highlight, and that is our classification module. So opening up that setup file is going to automatically open up our classification module. And again, I've selected the same data file that we were just looking at before. So if you want to build a classification library, if you click this little button up here, it will allow you to create a new class. And so I'm going to call this rock1, and just sort of an arbitrary name. I'm going to give that rock a color. rock 1 is going to be red. And I'm going to click somewhere on what I call my seed pixel. And so wherever I clicked, it's going to use as a seed pixel, and it's going to compare that seed pixel, the spectral response of that seed pixel, to the spectra of all the other pixels in the image, and it's going to, within a certain threshold, find all of the pixels that match that and create an average spectrum of all of those pixels together. So now, if I click this Update Spectrum button, it's going to give me that average. And so I can see that maybe there are some extra pixels that I don't want to include in there that are from a different rock. So I'm just going to exclude the recent region spatially. And if I click recalculate, all of the red pixels are within my threshold, but they're being excluded spatially. And all of the green pixels are being included in my average. And you can see here what my seed pixel looks like and what my calculated spectrum looks like at the end. And that calculated spectrum is the average of 2,576 spectra. And you can see that I must have clicked on a seed pixel where there was a bit of glare because my seed pixel intensity is a bit higher than what the average ended up being. But now if I end up clicking classify, so it goes through the image and it compares all of the pixels in the image to your reference library, and it will assign a color to every pixel that matches within the set threshold. So if I change that confidence interval, let's say I move it up to 97. Now, less pixels are included because they have to be a tighter match to what I've shown. And so now, again, just quickly, I'll do rock 2. Give it another color, say this one is white. I'm going to click on this bit of rock right here, update Spectra again. And here, within this threshold, a lot are included. And so now I'm going to lower the threshold here. Oh, shoot. I should not have clicked that. Okay. And I needed to click recalculate. And so now, instead of update, you can see that mostly only that little part is included in this new reference. And so now I'm going to click update on this new reference. I'll save our references and I'll hit classify again. And now you can see the two different colored, two different classes showing up in this image. And what I cheated and showed before was before everybody came in, I took a scan and I applied it to a reference library that I had previously built. So I'm not going to make you sit through me creating all of these classes in front of you here. But you can see that basically the different mineralogy in these rocks has distinct spectral character that can be identified. And we can assign a different color to each of those different spectra and have them show up in our false color image. And so basically that ends the brief introduction to the lab scanning kit. And again, anybody that wants to touch, feel, run this lab scanning kit after we're done, I welcome you to do that. This is another different scan of the same 4 rocks using that same spectral library that I built. I gave a little bit of identity to what these are because some geologists did tell us what this was, what this little part was, but not necessarily what all of the little spots were on the other rocks. And so here also you can display what the spectrum of each class looks like. And so this is what each of these different spectral features looks like. So this is the average reference spectrum in each of those cases that has been being used to identify these different spectral features using spectral angle mapping. And so now that we've briefly talked about the lab setup a bit, I'm gonna kind of switch gears again and get back to the remote sensing world. So if all the people that are live in the room turn around and look next to my colleague Charlie, that's one of our drone systems with a co-aligned Veneer SWIR sensor and a LiDAR all set up on a DJI Matrice 600 Pro. So that that turnkey package right there is set up to simultaneously collect Veneer data from 400 to 1,000 nanometers, SWIR data from 900 to 2,500 nanometers, and LiDAR data, all on a DJI Matrice 600 Pro. And it also comes with a high-performance GPS in order to orthorectify the data afterwards as well. And we just wanted to kind of bring it so everybody could at least see what it looks like. And we did fly this yesterday in conjunction with the Neon group to compare the results of our sensor with their very nice system that they have flying on a manned aircraft. So briefly what we did is as close in time as possible, we flew our drone over a scene with a couple of calibration tarps out there at the same time that the Neon Avarice system was flying over the same area. And I do apologize, I have not had time to work up all of the data since yesterday, but shortly we will have reflectance data, at least from the Headwall flights, and then when the Neon data gets processed as well, we'll compare the two data systems to kind of and of course, the Neon system is a top-of-the-line custom system, and so we don't exactly expect to beat them, but we hope to show that we can get some comparable data to what that system is collecting as well, again, at a lower altitude, higher resolution data collection. I guess the Neon group can speak more to that, but they are the ones using the Avarice system. Headwall did not use the Avarice system, but the kind of one of the parts of this trip out here was to compare the Avarice system to the Headwall system. No, the Avarice system is in a manned aircraft, so they must fly higher. We can compare the reflectance data that's gotten off of the targets. So we flew over standard reflectance targets, and we will compare the spectral data. The audience was asking whether or not the two systems flew at the same altitude and how the data could be compared at different. So they were not flown at the same altitude. The Avarice system was flown at about 1,000 meters on a manned aircraft, and the Headwall system was flown at 120 meters on a drone. And so the Avarice system is spec'd at about 1 meters spatial resolution. When the Headwall system is flying at 120 meters, the ground sampling distance will be roughly 7 centimeters or so. And so basically the spatial pixel size will be very different. But we flew over standard calibration targets, and we will end up comparing the reflectance data from one system to the next, and also showing that the Headwall system will have much higher spatial resolution because it is flown much lower. So the one in the upper right-hand corner is our co-aligned Veneer SWIR system that you can see on the table back there. We also have a nano hyperspec, which is just our visible or Veneer sensor from 400 to 1,000 nanometers. And down here is the micro SWIR sensor. So the co-aligned system has a micro SWIR and a nano both put together in the same box. And of course, well, LiDAR can be added to either this co-aligned system or the nano system as well. And for ground-based remote sensing systems, we also provide pan and tilt or rotation stages to basically, you get your motion by sweeping the camera at an angle across the scene. So now I just briefly wanted to talk about the data types that you gather in a hyperspectral data system, the different sorts of data processing that are done, and ultimately what we're looking for in reflectance. So what will be gathered at the sensor is always the raw data, the raw digital number. The sample is, or the sensor is going to detect a certain amount of light. It will convert that light to some sort of signal, a voltage, a current, and then that either voltage or current will be read out by the electronics, and it will tell us basically how much signal is actually getting to the sensor. And that will depend on the light source, it will depend on the optical characteristics of the system, it will depend on the detector characteristics, atmospheric absorption, and on the sample properties. So if there's any non-uniformity in the detector properties, if there's any non-uniformity in the optical performance of the system, that will all show up in the raw data. So if we convert the raw data to radiance, generally using a radiometric calibration. So with all of our systems, Headwall does offer a radiometric calibration. This must be done with the whole system altogether. So the radiometric calibration calibrates for a specific lens. So we will need to put the lens that you want calibrated onto the system and then run it through our calibration procedure. And the radiometric calibration will be a measure of actually how much light is reaching the sensor per solid angle. And that will include properties of the light source, the atmospheric absorptions, and the sample properties. Again, and so the radiometric correction will eliminate any detector characteristics. It will eliminate any system optical characteristics. And so kind of the striping that you can see in here that is due to differences in basically different lines in the detector is taken out in the radiometric correction. And I guess I also just want to note that in the SWIR range, there are a couple of bits of the spectrum that are always missing due to atmospheric absorptions. And finally, if you convert from radiance to reflectance, which is basically the amount of light reflecting off the sample divided by the amount of light hitting the sample, that only depends on the sample properties. This is generally always the ultimate goal that we want. And so again, you might get some not low numbers because you have very little signal, but you're also dividing by basically 0. So nonsense stuff is going to happen in the atmospheric absorption regions, even after you convert to reflectance. I guess I would just like to mention that because I often get people coming back to me saying, hey, I looked at in 1900 nanometers and it looks funny. What's going on? I was like, well, you don't have any light there, so you can't really analyze the data there. And so basically, this is just a brief sort of going from raw to radiance to reflectance. And this workflow is all set up in Headwall software as well. And so now I'm just going to briefly talk about ground truthing and how you kind of analyze hyperspectral data. So often when you collect a hyperspectral image of a large scene, you end up with this data cube where you have a spectrum at a bunch of different spatial pixels, and that spectrum will depend on the optical characteristics or the chemical characteristics of whatever your sample is under there. But one of the most difficult part for the scientist is to assign that spectral response to something that you're looking for. So am I looking at the spectral response of dolomite, calcite, goethite? And so basically, when I'm analyzing a data set, I can fairly quickly find all of the different spectral signatures. But then the hard part, well, one of the hard parts or the ground truthing part would be taking that spectral signature and identifying what it actually is. And that we generally call the ground truthing. So I basically just introduced that because now I'm going to show some remote sensing data where I did what I call kind of my initial analysis where it was not ground truth, and I just found all of the different spectral signatures and created a false color image of all of the different spectral signatures that I could find in the scene. So these images were taken at Saginaw Hill, which is a mineralogically interesting site that scientists at the University of Arizona are studying. And so this bit of data collection was done in conjunction with the University of Arizona. Headwall collected the data. Arizona is doing most of the ground truthing analysis. And I guess I did this initial characterization. So this is just a camera phone RGB image of what we were looking at. This is kind of your quote SWIR RGB image where the red is 1597, the green is 1203, and the blue is 1040. And so again, because there's no red, green, or blue, that's why your plants are kind of bluish and the rocks are still kind of brownish, but basically the red, green, and blue are just sort of arbitrarily chosen. So now, if I went through and I identified all of the different spectral signatures in that scene, I created a false color image and I just assigned arbitrary names to all of these different spectral signatures, some of which you don't see here because I created one, basically a spectral library for all of the different scenes that we scanned, and I'll show those other scenes in a second. But I guess this is first kind of the broad overview of the hillside. and I made all of the vegetation green just so you wouldn't get a bunch of dark areas at the bottom of the screen. So now this is an outcropping, which should have different mineralogy to it. And we do see different minerals showing up in the outcropping that we do in the kind of overall field. And finally, this image was just, there was sort of a pile of rocks that was nearby the feet of the people gathering the data. And they said it would be interesting to scan that pile of rocks. And one of the geologists there happened to have a copper rock in his pocket that was not native to the region. And he just threw it in the pile and said, hey, I'm going to throw a copper rock there. You scan it, and let's see if we can pick out that copper rock compared to all of the other indigenous rocks there. And if we could not, I wouldn't be telling you about it right now. So yes, this was the sphere. We scanned it with our pan and tilt system. So with a constant angular speed, yes. So here in kind of the darkish colors, you can see all of the native rocks where I assigned arbitrary names, and the cyan color, we made the copper rock that, so it's fairly easy to find the rock that doesn't belong in the pile of other rocks. And then our friends at the University of Arizona did some ground truthing to this data. So this is just a brief hand-waving overview to what they've done, but basically they assigned most of these different minerals that I saw here to different types of sericite. And they said the different spectral characters that we saw were because there were different amounts of sericitic alteration in these different minerals, but in kind of a broad sense, they would all classify it all as some sort of sericite. I'm basically just repeating what they told me there, so I'm no biologist, I'm no geologist, so I guess that's just sort of briefly what that was. And also on this yellow feature in the outcrop was either illite or smectite, and they said that because of the atmospheric absorption at 1900 nanometers, the spectral feature that could definitively distinguish those two minerals was kind of obscured. And so that's unfortunate that we had to have air in the way there. And the copper rock was a mix of chrysocolla and malachite. And so now this is just another sort of brief example of when we flew over a leach pad. So this is, again, kind of mining-like data. And the ground truthing of this data is still basically being worked on. So I can't show you the ground truthing data, but I can show you the sort of first pass at classification and all of the different spectra that were that make up this classification of the leach pad. So we did find, of course, a bunch of different mineralogy in the leach pad, and we're counting on our partner geologists to identify what those minerals are and what interesting information can be pulled from these leach pad scans. And so now, before I end this talk, I just want to briefly talk about Headwall's combination of LiDAR and hyperspectral imaging. So for those of you that are unfamiliar with LiDAR, it is akin to radar, where radar is radio detection and ranging. LiDAR is light detection and ranging. So essentially what LiDAR does is it sends out a laser beam and it counts how much time it takes for that laser beam to get back to the sensor. And that will very accurately measure distances. And as you fly over a scene, you can collect many of these laser pulses, and basically it will give you a bunch of returns to tell you how far away all of the different objects are in your scene and give you a really cool three-dimensional map of what your scene looks like. And so this is an example of what some raw LiDAR data looks like. So our standard LiDAR is a 16-channel system. So that means it has 16 pairs of lasers and detectors that are always firing and spinning around in that bluish silver box over there. And here you can see a stripe from each of the 16 lasers. And as you fly along, those lasers will basically gather more and more data, fill in all the blanks, and the final product will be a three-dimensional rendering of your scene. Okay, so I guess in one of the key features to that, one of the key advantages in terms of hyperspectral data is that, and again, I apologize for not getting into this, but I guess I don't want the talk to go for 3 hours. So I'm not going to dive deep into orthorectification, but part of the data processing procedure of this hyperspectral data is to orthorectify it, which will help to get out a bunch of the detection anomalies that happen as you're line scanning and your system is on a drone and it's kind of moving back and forth. And so before you orthorectify, your image will be very wavy. And in order to orthorectify, you need what is called a digital elevation model. So it's basically a map of what the elevation of the terrain is that you're going over. And you can use that to accurately calculate the distance between what you're taking a picture of and your sensor. And so the more accurate that contour map of the ground is, the better your orthorectification can be. And kind of your standard digital elevation models available through the USGS or other online sources gives you about 30-meter resolution or so to these digital elevation models, where if you're taking a ground sampling distance of 5 to 7 centimeters, you're often going to want better than 30-meter resolution in those digital elevation models. And so using the LiDAR data, now we have a 3D map of the scene that we just scanned over, so we can create our own much higher resolution digital elevation model that includes everything in the scene and stuff that might have been added since the last survey was taken, and give a much better orthorectification. And so these are just some images of LiDAR data that was gathered over a steep hillside. So you can see the higher part of the hillside is in red and the lower part of the hillside is in blue. And this is just, again, an illustration of turning this LiDAR data into a digital elevation model that, again, is taken care of in Headwall software. And I like to show this because if you're flying over that hillside and you're using the standard 30-meter USGS digital elevation model, you're not going to do a great job of orthorectification, because going from the top of the hill to the bottom of the hill, the distance, you're not going to very accurately measure the distance between the detector and the ground. Where if you use a LiDAR DEM, you get a much better orthorectification of the data. So this is the exact same data set, just orthorectified using different DEMs. And so with that, I'd like to thank everybody for their attention, and basically just briefly say, so we talked about, we gave a brief introduction to hyperspectral imaging. We talked a bit about LiDAR. We showed a live demo of Headwall's lab scanning kit, and we talked about some of the applications of hyperspectral imaging to the mining world. And with that, I'd like to open it up for questions from the audience or questions from people joining us from the webinar. So thank you very much. So the question was, can you purchase a single sensor and transfer it between the lab system, the drone system, and say your pan and tilt system? And I guess the short answer is sometimes. So if that is a demand of the customer, Headwall will work with you and develop a system that can do all of that. Currently, our nano hyperspec system is the only one that out of the box can transfer between all 3 of the systems. And we have had customers that have moved the shortwave infrared system, so that system right there, from one to the other. But I guess I would say that it does involve, it's not a quick snap in, snap off. You have to undo some bolts and put it on the next system. So I guess I will say, in general, yes. Some of the systems are more tightly engineered than the others, though. The question was, do you have a preferred type of light source? And was asked if we want to use LEDs. And so we absolutely do not want to use LEDs, because those will often have spectral bands and will be missing much of the different spectral features. So if you look spectrally at your LED light source, it will not be a continuous spectrum across the whole range that you're looking at. And so the artificial source that we use on our lab scanning kit is a quartz tungsten halogen lamp, and that's generally what we recommend. And as you can kind of see that in there is just sort of a standard quartz tungsten halogen bulb, but we've attached it to, well, we've also put in an aluminum reflector that focuses the light down to a line, because at any point, we're only gathering a line of information. And so we'd rather have all of the light in a line than kind of a broader light source that's just lighting up the whole scene. And how do we match the spectral library from the ground to the lab? I guess there are a couple of different ways that you can do that. And I guess, unfortunately, the most common answer would be in the data processing of your own software. So you could upload a spectrum that you gathered in the lab into a classification model and apply that against your whole scene. The way that I prefer to do it, or the way that I have done it in the past, is I'll do that first classification that I did, where I got a reference spectrum for all of the different things in my scene, and then I would compare those reference spectra against a library. So instead of comparing a library of 1,000 spectra against 1,000,000 pixels in a scene, I compare a library of 1,000 spectra against, say, 10 reference spectra. And then it is basically a smaller problem to solve. So I guess the short answer there is that it would be mostly up to the scientist to compare what they got in the lab to the spectral responses in the system, or in the hyperspectral data, to kind of get positive matches on the ground truth. So we are gathering GPS IMU information for every line that's gathered. So again, like you said, we have the SBET for to correct the roll, pitch, yaw, latitude, longitude, altitude of every pixel. And Headwall uses proprietary algorithms to apply all of our GPS IMU data to combine them with our digital elevation maps to orthorectify, kind of automated within our software. Yes, so we do, if we sell you a turnkey system, so a system integrated onto our drone, we always fly it before it ships out the door. And so we'll set the orthorectification offsets ourselves. And so when it ships to you, it will have kind of a standard orthorectification offsets already in there that were made at our facility, but you do, yes, also have the ability to adjust those those offsets from scan to scan to kind of dial in if there are slight differences from one run to the next. The stuff that we send it out of the box is always a good starting point, but I would recommend on almost every time that you collect data to dial it in a little bit, to basically change it, because you can almost every time, if you just change the numbers by the 100th place or so, you can get it a little bit better. So we have found that our radiometric calibration is very stable, holds for a very long amount of time. And basically, I would say you need to re-radio cal if your lens gets really dirty. Basically, what I was doing when I was measuring that white spectral on tile was getting a full frame white reference and kind of skipping the radiometric calibration part. So if I can fill up my entire focal plane with a white reference whose spectral qualities I know, I don't need to apply a radiometric correction before I just convert straight to reflectance. So I'm essentially doing a pixel by pixel correction based on the measured white target there. But usually in remote sensing, I can't have a tarp that's big enough to fill up my whole scene. No, I guess I've never scanned Scotchlight. So sorry. Yes, so every time data, so I guess I'll go with the remote sensing example. So normally in remote sensing, you're gathering a lot of data over a fairly large scene. And those can end up being very large data cubes in the end. So generally what we do is we pre-program a number of lines in there And after usually 2,000 lines, we will write a data cube, and then we'll start collecting another one. And that would make it so if you're scanning a really large field, you don't end up with one 60 gigabyte data cube. You end up with 61 gigabyte data cubes that are much easier to handle with a normal computer. And all of those data files would be saved in that folder. And the first one would be raw_0. The second one would be raw_2000, and so on and so forth, where that number is always the first line of the total data collection in that scene. And so the thing that in the remote sensing that you would get at first, it would just be the raw data. So that's what would come out in that data folder before you did any processing. And that raw data will be in an NV format, so you can use it in our software, you can use it in NV. And then when you go on to do, if you do the radiometric correction through our software, all of those raw data files would be, you'll get a new data file that would be raw _RD _0 2000 whatever, and that would be all your radiance files. And then you would generally find your white tarp in the scene, create a scene white reference, and use that as your white reference to do your reflectance correction from the radiometric data. And then you would get a data cube that's raw _RD _RF. And so all of those data cubes would be individually selectable. And this is all before orthorectification. And so then usually I would only orthorectify the reflectance data because that's what I care about. And then you would finally end up with raw _RD _RF _OR for all of your data cubes. And of course, say you started with, again, your 60 gigabyte data cube, you convert to radiance, and then it will be a 120 gigabyte data cube. You make a reflectance data cube, that will be another 120 gigabyte data cube, and then you orthorectify it, and it will be even bigger depending on the latitude and longitude conditions that orthorectification was done under. Did that answer your question? Perfect, right. Probably more than you wanted. The black part is actually the spectrograph. The camera portion is the white portion. So that, because that's an MCT detector there, and so it has a Stirling cooler in it, so that's why it's a little bit bigger. And the spectrograph is actually quite small. It's just the black part. Yeah, the veneer is about a 3-inch cube. And both one of those and the 3-inch cube veneer are in that system that's behind you. Along with a high-performance GPS IMU. Yeah, so if you hear that little hum right there, that's the Stirling cooler going in there that actually is keeping the focal plane at 150 Kelvin. We do not cool our spectrograph, and so actually cooling the spectrograph is probably what costs you a bunch more energy on the neon system. And so we don't do that because of a swap problem, that once you got a cooler that would cool the whole spectrograph as well as the focal plane, it would be too heavy to fly in one of those drones. About 5 minutes or so. It of course depends on how long it's been since you turned it on, but from warm to cooling down the focal plane, yeah, roughly 5 minutes. I'm gonna turn that one off and we'll wait a little bit and then we'll turn it back on. Oh, yeah, Charlie's got one over there. It doesn't really tell you, but if you, yeah, that's the drone. But yeah, if you hear the loud humming right now, it's because the cooler is working a lot harder to cool it down, and then you'll hear it go boo. And I guess I should repeat the question, but the question was how we get SWIR wavelengths, because the neon sensor needs to be cooled, and the answer is our sensor also needs to be cooled, and we use a Stirling engine to cool our sensor to our focal plane to 150 Kelvin. It's all through a graphical user interface. We don't have a command line thing, but we do have it all set up in batch process. So if you have like 60 data cubes in there, you can select all 60 data cubes and say convert to reflect or convert to radiance, and then you need to select all the radiance cubes and say convert to reflectance, and then the same for orthorectification. The question was, what is the optimal altitude and ground sampling distance to use when collecting these remote sensing data? And so our co-aligned system, just as an example, if you fly at roughly 20 meters, which is what I would recommend is probably the lowest altitude that you should fly at. If you go much lower than 20 meters, you can start feeling the wind from the rotors, and also our lenses are set to infinity focus, and much closer than 20 meters, you could push it a little bit, but much closer than 20 meters, you're going to start not being in focus anymore. And so if you're at 20 meters, you're going to get just over 1 centimeter pixel size. I think like 1.3 or 4 centimeters, if I'm pulling it off the top of my head. And then the highest a drone can fly without special permission from the FAA is 120 meters. And so if you're flying at 120 meters, you're going to get just over 7 centimeter ground sampling distance. About 1.3 times 640. I mean, you can put that in an airplane as well. So it has its GPS IMU and thing. I should say you can't put the light. Well, you could put the LiDAR in the airplane, but the LiDAR wouldn't do anything because it's not a powerful enough LiDAR for that. Yeah, you can, through our software, you can adjust the flight speed, all that. Yes, yeah, we have little calculators in there that will, based on your frame period, tell you what your flight speed should be depending on your altitude. You could use multiple scene white references to, yeah, if you flew over the tarp multiple times and had multiple white references, you could do that. That would of course be a manual procedure because you need to assign the correct white reference to the correct time. Generally, our flight control software holds the drone at a fairly steady speed. So you mean like if I'm going over terrain where there's a huge jump and then I'm basically pointing straight up in the drone? I guess the best practical example I can show of that is the one that I showed earlier where we flew over that hillside that you saw and then used the question was, does the drone have trouble holding a steady speed when you move when you fly over terrain where there's a large change in altitude? And kind of a real world example that I can show is this data was collected over a large change in altitude. This is the LiDAR data that was collected. And then again, this is the LiDAR DEM that I showed you. And this is the hyperspectral data, again, showing with the USGS 30 meter DEM versus our LiDAR 10 centimeter DEM. And we really did not miss many pixels or anything here. So yeah, I guess I would say empirically, our flight control software works pretty well over a fairly steep change in altitude or change in height. Yeah. And usually the course DEMs work just fine, but if you're changing the altitude so drastically that then you're going to have a problem. And Brian is referencing pricing for the co-aligned system there, I assume. Okay, so the veneer will be much cheaper. The sphere is usually the more expensive system, and the co-aligned has both of them in the same package. And I guess at this point I have a couple of other questions that came from people online that I think I've been ignoring for a while. So the first question was, can I open your data with other software like Envy? Yes, you can. All of our data is in the Envy format, so you can, of course, specifically open it with Envy. We've opened it in a number of other softwares, such as MATLAB, and so the header files will have all of the information that you need to open it up in your software of choice, and they all are Envy compatible. The other question is, once the flight plan is set, does the drone fly the pattern to acquire the data? And the answer to that is yes as well. Through the flight planning software, the UGCS flight planning software that we use, you can set a flight plan, and we of course always recommend that you pre-program a flight plan and have the drone automatically fly the flight plan rather than trying to manually fly it, because the computer will always be better than you. So we do not generally use an atmospheric correction. We use a reflectance tile that we put out in the scene. So yeah, our recommended way, we sell a reflectance tarp that has 3 panels on it, one with 11% reflectance, one with 30 or 33, I can't remember, but about 30% reflectance, and the last one with 56% reflectance. So depending on the properties of your scene, you can pick the appropriate tile to use for correcting the data to reflectance. And it seems like we're running low on questions, but I would also love to give anybody the opportunity to play with the starter kit if they want to as well. Sorry, people joining us remotely, that's going to be hard for you to do.
Hi, this is Brian Lorfing, the Territory Manager for the Western States. We're going to go ahead and conclude the webinar now, and I'd like to do a shout out to John Adler of Patel and Neon, Joe McGinley, and Brian Johnson at the Earth Lab have been great in helping assist us with this. And I'd be remiss if I didn't say Dr. Will Rock, who did an amazing job today and always does. Oh, it's Will's birthday. I just found that out. Happy birthday, Will. Our chief pilot, Charlie Kepler, as well. Really appreciate all the work everyone has done, and thank you guys for your attention and your time. With that, we'll go ahead and conclude and have a good rest of the day. Thank you.